The name of the program is "It's in the Way That You Use It," after the old Eric Clapton song. I bet you maybe you thought you were going to hear the Eric Clapton song, but it being the Super Bowl, we wanted to get revved up with some Dropkick Murphys, so that's just the way that goes. But as this applies to variable speed circulators, you see different types out there. There's pressure regulated or delta P type of circulators. There's delta T circulators, which TACO is the only supplier of those residentially here in the North American market because it's designed for the North American market, a delta T type of variable speed circulator. A delta P circulator reacts to changes in pressure differential within the system, i.e. zone valves opening or closing, or thermostatic radiator valves modulating. Okay, that's what tells that circulator to speed up or slow down. We'll get into the specifics of that in a moment. What a delta T circulator does is it has a sensor on the supply and return. You program it for a specific delta T for which the system has been designed. That's the key. The delta T you select must be the one for which the system was designed. Generally, it's a 20-degree temperature differential. And what you'll see happen is that the circulator will speed up and slow down to try to maintain that temperature differential, meaning the triggers that'll slow that pump up or speed that pump up will be zone valves opening or closing, as well as changes in outdoor temperature, which means changes in the load. We'll be taking more energy out of the fluid. When it's colder out, the pump will, as a rule, tend to run faster in those colder times. So those are the triggers that make these pumps go faster or slower. Will they all work in all applications? Absolutely. They'll all work if you define work as, yeah, I'm going to provide BTUs. No one's going to call me up because they're freezing to death. So my job is done. Yeah, both pumps will get her done for the most part, depending upon how well you program them. But will they do the most possible for your systems? What do I mean by that? Will they enhance the capabilities of the system in terms of comfort, efficiency, and economy, or will they limit the capabilities of a system in terms of efficiency, comfort, and economy? There's two ways of looking at it, and how you apply those will determine which way they go. You may have a pump that will enhance and maximize the comfort, economy, and efficiency of a system, while the same pump in a different application might limit the comfort, economy, and efficiency of the system. So you've got to be careful. You've got to understand how they work, what they do, and for which applications they were intended. That's when you can start to put these things in the right place and know the difference between the two. It's important for a pro to know what he's holding in his hands and why he's putting it on this job and why he might want to put a different pump on that job. Very, very important. Brief editorial comment. A lot of folks call these smart pumps, and I think, yeah, you can, but it's a dangerous name because, quite frankly, neither of them are all that smart. And here's the bottom line. Neither of them are so smart that they replace you. They replace your knowledge, your understanding of how to best apply these things. Yes, there is some adaptive intelligence built into both, but they don't do the thinking for you. I've heard trainers out there say, oh, these pumps are great. They do the thinking for you, or they take the thinking out of it. And I can't imagine a more dangerous statement for someone to make. They absolutely do not take the thinking out of it. And what's more, I don't think we want to take the thinking out of it. If we have products that take the thinking out of it, then by gosh, as professionals, what are we worth? Okay? These circulators don't take the thinking out of it. You've got to know what you're holding in your hand, and more importantly, why you're holding it in your hand. Okay, that's the editorializing. Enough of that. I will move on. Okay, I will move on. So let's go. It's in the way that you use it. Why? What are we talking about when we're talking about variable speed circulators? First, I want to get on the table the different types of variable speed circulators, pressure regulated delta P versus temperature regulated delta T. Where do they come from, and for which applications are they most appropriate? Now, delta P circulators, whether the Velo Stratus Eco, the Grundfos Alpha, those are of European design, and they were intended for European type systems. Delta P circulators are uniquely equipped for this type of a system that you're looking at here. Your typical European residential hydronic system includes panel radiators with thermostatic radiator valves. They don't have on-off thermostats. They don't have a thermostat that turns the system on, and when it's satisfied, it turns the system off. That just really isn't done over there for historical reasons, not because it's better, not because it's more efficient, just because when they started installing central heating systems, they were retrofitting older homes. It was enough of a challenge to run the pipe to each room. Who had time to run thermostat wire? So what they would do is they'd have pumps run continuously, and each panel radiator had its own thermostatic radiator valve, which acted as a room thermostat. But these things weren't on-off valves. They were modulating. They would be opening or closing. Very rarely would they be fully open, and even more rarely would they be fully closed. Okay, but that's the type of systems that were installed and are still being installed in Europe. Panel radiators, thermostatic radiator valves, with circulators running 24/7 for a period of about 8 to 9 months. So again, your typical European system has thermostatic radiator valves, no thermostats in these panel radiator applications. Pump runs all the time, boiler bounces back off of its outdoor reset control, but the pump does run all the time. You will see the statistics of circulators in European systems that will be on for 6,000 hours. In fact, the efficiency labeling that the European Union puts on circulators from Europe, you'll see them on the ones that you may see in supply houses here, where they have these A, B, C, D ratings. You know, the A is the most efficient. Those ratings are based on 6,000 hours of continuous operation. If you're going to be running a circulator for 6,000 hours continuously, and you're paying upwards of 30 to 35 cents a kilowatt hour for electricity, you darn well better have an efficient circulator. That's where ECM comes from. Here in the U.S., we do something kooky, crazy, and completely out of control. When we have enough heat in a room, we might tend to shut the thermostat, or shut the circulator and shut the system off. I know. Nuts. Why would you do that? But yeah, enough heat, let's turn it off, because after all, the most efficient circulator in terms of energy consumption, electrical consumption, is the one that's off. It doesn't use any electricity then. Believe it or not, I got into an internet argument with a guy who tried to argue that leaving a pump running continuously is in fact more efficient when it comes to electrical consumption than turning it off every once in a while. I'm sorry, there's not a mathematical formula in the world that'll bear that out. 2,500 hours versus 6,000 hours. Do the math, man. Shut the pump off and it's better that way. But these are how they do things over there. They don't have thermostats. The pump runs continuously. Thermostatic radiator valves modulate for each room. Your Delta P type of circulators that respond to thermostatic radiator valves opening or closing, are perfect for that type of an application, particularly what we would call a proportional Delta P circulator. Proportional Delta P, you may see the pump curves, it looks like an inverted V. As flow goes down, the head pressure created by the circulator, the head pressure differential created by the circulator also goes down. That's what Delta P was invented for. That's what it was developed for. That's its application. Uniquely qualified to do that. Perfect application for it. Understand the trigger that tells a Delta P or pressure regulated circulator to go faster or slower. Let me poll the group here. Why don't you throw that? Give me an answer if you know how a Delta P circulator speeds up or slows down. And Greg Towsley, just type it in if you know what is the trigger that tells a Delta P circulator to speed up or slow down. We'll see where you're at. Greg Towsley did ask, isn't your Viridian from your new relationship with Ascol an Italian-European circulator? Yes, it is. It's a Delta P circulator. It has 3 functions, which make it kind of interesting for us to add into our mix. But yes, absolutely, it is a pressure-regulated circulator. And we'll explain some of the applications for it when we get to it a little bit later on. But let's see what you got. Change in pressure, head pressure, pressure drop, impeller. Okay, what makes it go faster or slower? Deb, I know you know this. Yeah, amperage causes the circulator to change speed, but how does it know? That's absolutely, technically that is correct, Lyndon. Amperage causes the circulator to change speed, but how does it know? John Lavelli says system load. How does it know? Delta P circulator, gang, has no way of knowing what the system load is. It has no way of knowing what BTUs are required. It just doesn't. There's no way of knowing. It infers certain things, but it has no way of knowing what the BTU load is on the system. It can't. It is amperage. Lyndon, you are correct. It is amperage. And Matthew, you got in there. It knows because it's an ECM motor. No, it doesn't know because it's an ECM motor. That's actually not the case. An ECM motor just is an ECM motor. How does it know what the load is? It really can't. The trigger that tells a delta P, or pressure regulated circulator, to speed up or slow down is resistance against the impeller. Here's an example. Thermostatic radiator valves modulate, right? They're opening or closing based on the relative comfort level in the room. If you see from the picture here, that is the thermostat, that little white head there with the 1, 2, 3, 4, 5 numbers on it. That's the thing that determines the comfort level in the room. The fact that it's sitting 2 inches away from the hottest thing in the room, to me, I always find that a little comical, but that's where it is. Okay, there's a little waxy element that forces the spring open or close, modulating to open or close that valve. So that valve is rarely fully closed. It's rarely fully open. It's always bopping back and forth somewhere in the middle. But let's say a circulator is running, and the TRVs, the majority of the rooms in that house are starting to reach their comfort level. The TRVs start to close. That puts more resistance. That increases the resistance against the impeller. That's a signal to the brains in the circulator to say, hey, wow, we have enough heat up there. I'm working harder to deliver heat. I don't need to work as hard. I'll just slow down. So those closing TRVs are a signal to that thermostatic radiator valve, or a signal to the circulator to slow down. It doesn't know BTUs. It just knows what these TRVs are doing. Now, if you have a TRV that's mostly closed, or if a room is cold, it doesn't know what to do. As the TRVs open, there's less resistance against the impeller. That's the signal for the circulator to go a little faster. ECM has nothing to do with it. It's just, and it's not a change in system pressure. Mike, I guess it's a change in system pressure. No, it's a pressure differential. It reacts to resistance. It reacts to head, okay, within the system. Okay, so a valve opens wider, creating a wider pressure differential. Actually, what it's doing is it's creating less resistance against the impeller, and that is a signal that we need to add more heat out there. So as we need more heat, as the TRVs open, that is an inferred signal that we need more heat in the system. The pump will run faster. As the TRVs close, that's an inferred signal that we need less heat. The pump will run slower. Okay, that's basically how they work. Now, what happens when some of the TRVs are opening and some of the TRVs are closing? And it just it reacts to the overall differential. Okay, it reacts to that overall resistance. So if you've got a bunch of rooms that need more and a bunch of rooms that need less, it doesn't know the difference. Okay, it's going to do what we are talking about. Does this work with zone valve applications? Very good question. Now, zone valves don't modulate. Zone valves are either open or closed. They're either open or closed. So what you have with a pressure differential circulator, all it knows is whether that valve is open or whether that valve is closed. So it's opening or closing. What will happen with zone valves, open, on-off, open-close zone valves that are run by thermostats? A delta P circulator is going to become a fixed pump curve circulator, meaning we'll get into the details of it a little bit, but the system will run where the system curve intersects the pump curve all the time. A delta P pump in a zone valve application will run the same speed in October as it does in January as it does in April when zones are opening and closing. It has no way of inferring otherwise. With TRV applications, a case could be made that it may very well run faster in December than it does, let's say, in October, depending upon the TRVs. That is a possibility. But zone valves, no, it doesn't know from load. It only knows open and closed. Okay. As a zone pump, a delta P pump just runs one speed. It's never going to vary its speed. It's going to run one speed whenever it comes on, and that's that. Let me just do a quick rundown. Does that make sense, guys? We had a lot of questions in here. Again, These aren't magic pumps. Just understand that. Neither delta T nor delta P are magic. They just react to something. Okay, they were with TRV applications with a proportional delta P curve. Okay, they react to opening and closing of these valves. The modulation, they react to the modulation, which is a good thing. In thermostat slash zone valve applications, they call them smart pumps. They actually are kind of dumb. They just open. They go one speed with 2 zones calling. They may go another speed with 3, another speed with 4, and that's that. They don't react very well to that. Okay, let me make sure that makes sense. Is there Ian McDonald asks, is there a pressure switch? Or does a delta P pump read torque? No pressure switch, no sensors. There's nothing inside there. It's just resistance against the impeller. It reacts to if the circulator sees that it has to pump harder or there's more resistance against it as TRVs tend to close. That's a signal for it to slow down. It's pretty simple. Okay, and as TRVs open, there's less resistance. It starts to go faster. I hope that gives you a good idea of how these things work. But in a proportional delta P mode, a delta P pump is basically good for thermostatic radiator valves. And that's about it, because that's what it's for. In the proportional delta P mode, that would be your Grundfos Alpha and auto-adapt. That makes it a proportional delta P circulator. Perfect application here. Okay, Velostratus Echo is a proportional delta P pump. Perfect application here. When you start looking at constant pressure or constant delta P pumps, now we might have some different places where we may be able to use that, as we will see later on. Now, when we look at U.S. systems, is there a typical U.S. system? I think U.S. systems are kind of like it's a melting pot. It's like, who's your typical American? Well, we're a melting pot society. U.S. systems are kind of a melting pot nowadays. Sure, you have, in many areas, you have your series loop of fin tube baseboards, and those are straightforward, either zone pumping or zone valves. Great applications for delta T pumping in both cases, as we shall see. But you might have cast iron baseboard. You might have radiators, convector units, radiant floor heating, fan coils, air handlers. Sometimes you have this all in the same system. So we're really kind of a melting pot of different types of systems, but one thread does seem to weave through most of those systems, certainly not all, but most of them, is that we do zone. We have thermostats to relays that control either zone valves or zone pumps. That tends to be the way we do things here, and for a very good reason. You got enough heat, shut the thing off. Okay? It's not a bad way to go, and it remains very comfortable. So that's kind of what we're looking at here. Multiple zones with circulators or zone valves are very, very common. By far and away, the most common types of systems here in North America. And typically, on average, nationwide, our run times for all of the moving parts, circulators, burners, blower motors, that sort of thing, 2,100 to 2,500 hours annually. We don't turn, 6,000 hours. Think about 6,000 hours. Turning a pump on and letting it run for 6,000 hours is roughly the equivalent of turning it on Labor Day and turning it off on Memorial Day. If you're trying to save electricity, why would you leave a pump on for 9 months? These things just boggle my mind, but people say, oh, it's the most efficient. I don't get it. I just don't get it. Okay. Alrighty, now let's get into variable speed circulators. Why would you use a variable speed circulators? Guys, you chime in on your end. Why would you use a variable speed circulator? Okay, give me some thoughts. Okay, why do you think you would use a variable speed circulator? No, Bob Kleinschmidt, I don't need you to send me a Seahawks jersey. I know you have extras. You type in your thoughts. Why would you use a variable speed circulator? Matthew Reed says, because they're freaking awesome. I'm with you. But what's the reason? What prompted you to do that? How did you get there? What were you hoping to achieve? What were you hoping to get? To match the load, to match the BTUs sent to the system as the load required? All very good reasons. There are different, but what circulator are you using to achieve that? Both Mohsen and Jeff, they do different things. Okay, some circulators say they do it, but don't really, to match the load, because you said so and you're the king. George, I like you, man. To minimize the amount of electrical energy used. Okay, to maintain a 20 degree. All very good answers. I think it's a good question. Why would you use a variable speed circulator? In many cases, it's probably you use a variable speed circulator for the same reason the guy who lives on that island has a car. Because he can, okay? Because you can. Best applications for variable speed circulators, zone valves or radiant floor heating with manifold actuators. That's a zone valve job. You could use them as a zone pump, One's going to vary its speed as a zone pump and one isn't. A delta P pump's not going to vary its speed as a zone pump. It's just going to find its happy place, and that's the one speed it's going to run because there's never any changing pressure differential when used as a zone pump. A delta T pump, however, will change its speed when used as a zone pump depending upon how cold it is. When it's colder out, you're pulling more BTUs out of the zone. Pump may need to run faster to maintain that 20-degree delta T. When it's warmer out, we're pulling fewer BTUs out of the zone. The pump may need to run slower to maintain that 20-degree delta T. So think about it in those terms. Okay, it does use that way. It does use electricity. Michael says to reduce system noise in terms of not having to use a pressure differential bypass valve. Michael, in most cases I found pressure differential bypass valves are band-aids for picking the wrong pump in the first place. If you use a steep curve pump when you have zone valves, a steep curve pump like any 3-speed pump, the Takeo 0015, the Grundfos 1558, steep curve pump, when you use it with zone valves, it's going to bang. If you use a flat curve pump like a 007 with zone valves, it won't bang. Okay, so it's just something to think about there. Okay, so zone valve or zone pump. A lot of folks, and some of you have said, we use them for electrical savings, and I want to put just an earmark on that so we don't overstate that. I've heard a lot of crazy comments out there. You're going to save so much electricity. You're going to cut your electric bill by tons, and the truth of the matter is, no, you're not. You're talking about an 80-watt circulator, like a 007, a 0015, a 1558. They're 80-watt circulators. They don't use a whole lot of electricity in the first place. Okay? To say we're going to cut that down is great. It's nice, but in terms of life-changing money on an annual basis, it doesn't amount to much. I've seen guys, extrapolate that out, over a 20-year period. You're going to save over $1,000 in your electrical costs, which is substantial, assuming the circulator lasts 20 years, or assuming you stay in the house that whole time to realize that saving. It's nice, it's a big number, but it's not immediate. There's very little immediate savings, tangible savings, and we're gonna illustrate that. Okay, we're gonna do that. Dave Carl says you use a variable speed pump to reduce the number of pumps needed in the system. One pump with zone valves. You can do that with a fixed speed pump too. Absolutely, you can do it with a 007 zone valve. So let's examine that. Now, hopefully, you maybe we'll get to see how that works. Let's talk about electrical savings. And let's say I have 5 zones, and I'm going to have a pump on each zone. Okay, 5 zones, 5 007s. They're 80-watt pumps. So 5 007s at 80 watts a pop. That's 400 watts worth of pumping power. Let's estimate the electrical consumption. It's pretty simple math. To estimate electrical consumption, you have to turn watts into kilowatts, and you do that by dividing by 1,000. Okay, 400 watts divided by 1,000, you get 4/10 of a kilowatt. Okay, that's the electrical consumption for these pumps. It's 4/10 of a kilowatt. To turn that into, to do our math, we now have to estimate our kilowatt hours. There's our kilowatts. Now, how many hours over the course of an average heating season do we expect this circulator to actually run? Now, this map comes from AHRI, and what this tells us is it tells us over bands of North America, what are we looking at for average runtime over the course of the heating season. And you'll see, like, look at just show this upper Midwest section here, the upper portion of Minnesota, upper peninsula of Michigan, and just northern Michigan and the Great Lakes. It says about 3,000 hours on average. This is testing done on boilers, furnaces, pumps, everything going back decades. And these are average estimates. What this tells us is the length of the heating season, not the depth. Okay, degree days, BTUs tells us how cold it gets. This just gives us an average about how long the heating season actually is. Okay, so 3,000 hours there. Now take a gander over here in the Pacific Northwest. Okay, Seattle. That looks to be about 3,000 hours too. Again, not how cold it is, but how long of a season might we actually have to run our heating system. Okay, you look at the cold weather belt of the U.S. from Maine, Vermont, New Hampshire, part of Massachusetts, New York, west to Pennsylvania, Michigan, Wisconsin, Minnesota, and then that little sharp left turn down into Wyoming and Colorado. You're talking about 2,500 hours. There's your real cold weather belt. Move south, you're down to about 2,000. Further south, it gets lower and lower and lower as we go. What we're going to take a look at, we're going to use this map, and we're going to put our let's say we're right here in Minnesota, okay, where I'm at. just outside of Minneapolis, St. Paul, about 2,500 hours. We'll use that number for an estimate. So 0.4 kilowatts times 2,500 on hours. Hey, you know what? If you think the pump's going to run longer because you have outdoor reset, throw it in there. Go up to 3,000. Whatever the number is the number. Okay? So 2,500 on hours in this case, that gives us 1,000 kilowatt hours. Now to estimate our electrical consumption, our cost, we simply multiply by the cost per kilowatt hour. Now here in Minnesota, we average about 9 cents a kilowatt hour. The national average is about 11 cents a kilowatt hour. You get out in the Pacific Northwest where they have a lot of hydroelectric, it's 6-7 cents a kilowatt hour. It's nothing. You get up into some parts of the Northeast, you might be talking 20-22 cents a kilowatt hour. Put your number in here to see where you're at. What I'm going to use here is a high average of 15 cents a kilowatt hour. And that tells us to run all 5 pumps. It's $50, $150 a year in this example. About $150 a year. That's 5 pumps. That's $30 a pump per year. Okay, per heating season, $30 a pump per heating season. If we divided that over, let's say, a 7-month heating season, you're talking about less than $22 a month. The electrical portion to run your pumps is about $22 a month on your heating, on your electric bill. Now, is that a ridiculous amount of money? Is that an outrageous amount of money? Is that an unacceptable amount of money? I don't know, but it's $22 a month. Would it be a good thing to cut that down? Yeah, it would be a great thing to cut that down. How much can we realistically save? Well, let's take a look. Let's go to the next step here. Let's just go from 5 pumps to 1 pump and 5 zone valves. And let's stay with the 007 because, gang, 95% of the hydronic systems out there can be running off a 007. And the 5% that can't, you look at a 0015, bang it up a couple of speeds, and you're going to be fine. You're going to be more than fine. 007, 80 watts, 5 of the Taco Zone Sentry zone valves at 1.44 watts each. We're looking at 87.2 watts, and you can see where this is going. Divided by 1,000, multiplied by 2,500. We're now at 218 kilowatt hours as opposed to 1,000. Ladies and gentlemen, we just cut the electrical consumption by 80%. How did we do that? We cut the number of pumps by 80%. That's the thing that bugs me about people say the only way to save money is with an ECM motor. No. Okay, we cut the number of pumps by 80%, we cut the consumption by 80%, and we've done this without going to ECM, okay, absolutely without going to ECM. 218 kilowatt hours, we multiply that by 15 cents. Now we're down to $32.25 a year. In that $30 to run the pump, about $2.25 to run the zone valves, okay? So that break over a 7-month heating season, that's about $6.50 a month. So we went from $20 to, say, a little more than $21 to $6.50. Okay, we saved about $14. 14. Let's call it $15. You save $15 a month on your electric bill. What can you do with $15 a month over the winter? I don't know. Maybe go to the movies by yourself once with a large popcorn, or maybe a small popcorn. I don't know where you go to the movies. That's the number we're talking about. That's the money we're talking about. It's not life-changing money. Let's take this a step further now and go with the ECM. Okay, 1 pump, 20 watts with 5 zone valves. We see where we're going here. We're down to 68 kilowatt hours. Hey, that's fantastic. That's way better than 1,000 kilowatt hours, and it's better than 218 kilowatt hours. We math that out at 15 cents a kilowatt hour. Now we're talking about $10.20 a year. You know, we're over a 7-month period. We're talking less than $2 a month. Okay, but what we've done is we've gone from about $6 a month to less than $2 a month. So maybe save about $4 a month, a little over $4 a month, going to ECM. That's the reality of the savings, gang. It's about $4 a month, standard pump to ECM pump in an apples-to-apples situation. $4 a month. You can't go to the movies by yourself for $4 a month. Maybe you can get a Happy Meal. I'm not quite sure how that works, but that's the reality of the situation. And this is really how people feel. They think they're going to be saving tons of money, but this is the reality. Now, you guys tell me, does that sound like a ton of money? Does that make sense to you? Again, I hate it when people say you're going to save a bunch of electricity, but the reality is that's not the case, and I think it's an inappropriate promise because that's really not what's going to happen. There are compelling reasons to use ECM, variable speed circulators. Electrical savings is nice, but it's not a huge part of the story. Now, up in the Northeast, you're seeing a lot of the utilities offer rebates, fairly substantial rebates, for using ECM circulators. That's not to save each individual customer money. there's a ton of pumps up in the Northeast, and if they can reduce the consumption, universal consumption of all of those circulators, that is a benefit not necessarily to the homeowner, but it is a benefit to the utility. Now, because we have all kinds of electrical stuff in our home now, way more than we did 30 years ago, the more they can reduce how much each home uses, the less likely they are to have to invest in new power plants and incur the costs that those bring on. So really, that's why a lot of the utilities are offering rebates for high efficiency anything now. It's not to save the homeowner a ton of money, because you know darn well the rates are going to be going up to offset that. They're not changing their income much. It's just they're just reducing what they have to produce, or keeping what they have to produce at a constant level, but reducing individual consumption so they can continue to serve without having to break ground. So that's just a way of thinking about it, okay? ECM expected life, asked Morgan, that's a really good question. If you don't treat the water, okay, the life expectancy is not going to be great. That's a given. These things are different. Okay, there's a big old magnet in ECM circulators, or electronically commutated motors. The way they work is they have a real powerful magnet. If there's magnetic crap in the water, guess where it's going to go? And that will shorten the life of those circulators. So you put these things in, gang, you need to treat the water. Those magnetic filters like Fernox has are absolutely essential. Okay, absolutely essential. Okay, and the question is the cost of a pressure differential bypass valve. I think it's kind of, I'm looking at the camera. I'm looking at the questions right now. I can look at the camera or look at the questions, Morgan, one of the two, okay? Cost of a pressure differential bypass valve plus installing it, plus how many trips you have to go back to figure out how to put it in. I mean, I think if you're comparing the install cost of an ECM variable speed delta T or delta P circulator compared to the cost of the wrong pump and a pressure differential bypass valve, I think that's a silly comparison. Again, the pressure differential bypass valves, 9 times out of 10, not 10 out of 10, but 9 times out of 10 that I've seen them installed, they're Band-Aids for picking the wrong pump, pure and simple. Someone put in a 3-speed steep curve pump where a single-speed 007 flat curve pump would have been a better choice. With that pump, they would not have needed the pressure differential bypass valve. So personally, I don't buy into the theory that if you compare the cost of an ECM pump compared to the cost of the wrong pump and a pressure differential bypass valve, it's a wash. To me, that's an illegitimate comparison. Use the right pump in the first place, you don't have that problem. That is my opinion. Okay, great. Now, let's talk about why the real benefits of variable speed pumping with a delta, let's say with a delta T circulator. We're going to get into delta T and why it makes sense. Because circulators have any fixed speed, or in the case of a delta P circulator, fixed pump curve circulator, okay, they have an impact on how the system works. And let's take a look. We're just going to use this as an example. It's a 70,000 BTU system. Okay, if we use the universal hydronics formula, GPM equals BTUH divided by your design for delta T times 500, we will come up with a requirement for this system of 7 gallons per minute. Okay, 7 gallons per minute, and we do our head calculations, and we come up with a total head for this system for the worst case zone. This is a zone valve system, the worst case zone of 5 feet. If we plot that on a pump curve chart, 7 gallons a minute, 5 feet ahead, it's right where that gray dot is. Now those black lines that start at 0, 0 and move up and to the right, those are system curves. Every system, hydronic system, has its own system curve. It has its own system curve. It's a unique fingerprint. And a zone valve system has a bunch of system curves. There's one system curve for all zones calling, and that's the one farthest to the right. It has one system curve for the one smallest zone calling. That's the farthest one on the left. And then it has a bunch of system curves for all the different combinations of zones that you could have. Okay, and they fall in between the two. Now, with a fixed speed circulator or a fixed pump curve circulator, like a delta P circulator, as we will see, the system will always operate where the system curve intersects the pump curve. Always, always, always. That's just physics. Energy in equals energy out. It has to. Okay? Now, we see 7 gallons a minute at 5 feet ahead. With this fixed pump curve that we show here. This is a maybe medium or even high speed for a standard 3-speed circulator. Okay, where is the system really going to work? It's going to really work right there. We need 7 gallons a minute at 5 feet ahead under design conditions, coldest day of the year. Let's say that's 0 degrees. Where is it really going to work? It's really going to work right up there on the pump curve where the system curve intersects the pump curve, 9.5 gallons a minute at about 8 feet ahead. What we're going to be doing here is we're not delivering 70,000 BTUs with 7 gallons a minute. We're delivering 70,000 BTUs with 9.5 gallons a minute. Remember, GPM equals BTUH divided by delta T times 500. The 500 is a constant, right? GPM or BTUH is a constant in this example of 70,000 BTUs. We also now have a constant of 9.5 gallons per minute. So the variable that's left is delta T. Delta T is not going to be 20. It's going to be something less. It has to be. It's just, you know, it's the only, and we can figure this out, okay, mathematically, because numbers don't lie. There's your math. There's your universal hydronics formula, and here we algebraically manipulate it to isolate for delta T. So delta T equals BTUH divided by GPM divided by 500. Let's fill in the numbers and see what the actual delta T is going to be. Again, we're delivering 70,000 BTUs with 9.5 gallons per minute. If we do that, we will find that the delta T for this system under design conditions, coldest day of the year, all zones calling, best case scenario, if we had temperature gauges, the best we'll ever see, best we're ever going to see is a delta T of about 14 degrees, a little less than 14.5, so right around 14 degrees. With a cast iron boiler, that means the water may be going out at $1.80, coming back at $1.65, okay, or $1.65.5, okay, $1.66 thereabouts. Condensing boiler, the water may be going out at 140 and coming back at 126, not 120. First off, for a cast iron boiler, what do you think that will mean? If the water's coming back a little bit warmer than you would like, what's that going to do to the boiler as it fires? And what's it going to do to a condensing boiler when the condensing boiler fires? You guys tell me, what do you think will happen? What's that going to lead to in terms of performance and for that boiler? So type them in. Anthony Reichel, short cycle. Sure. You're going to promote short cycling. Okay, you're going to promote short cycling for the boiler. And everybody else is chiming in too. Yeah, absolutely. You're going to promote short cycling. And with a condensing boiler, you warmer water temperatures than you like, that boiler's not going to condense as much. It's not going to be as efficient maybe as it could or should be. Okay, so let's take a look at one zone calling now, 10,000 BTUs, like a small zone, 1 gallon, 10 gallons, 10,000 BTUs, that would be 1 gallon a minute. Let's say that it just happens to be the longest zone at 5 feet ahead, just for giggles and grins. That's where you want to be with this pump. It's really going to be working up there. About 16 feet ahead, that's why zone valves bang, closing against that kind of pressure differential. But I'm also looking at about 2 gallons a minute. So now I'm delivering 10,000 BTUs, not with 1 gallon a minute, but with 2 gallons a minute, and the numbers still don't lie. We fill in the blanks over here, and we find with one zone calling, the delta T is going to be 10. So this is 0 degrees outside, coldest day of the year. The best we're ever going to see will be delta T's popping back and forth between 10 and 14.5. What will happen? Well, coldest day of the year when the boiler should be running the longest, this is what you get. Anybody know what that is? That's a short cycle. Get it? Short cycle, small bike, short cycle. Come on, man. I looked for that online for about 2 hours before I found just the right picture. That's a short cycling boiler, man. That's a short cycling boiler. And that's at 0 degrees design conditions. What happens when it's 35 degrees outside? Cut those numbers in half. The delta T in the system is going to bop between 5 and 7.5 degrees. Okay, and we're going to short cycle like crazy. We don't like that. That's no fun. That's not good for the boiler. It's not good for efficiency. It's not good for economy of operation. It's not good for the lifespan of all the moving parts if they short cycle like that and wear out. So what do we do about it? Well, here we look at a delta T circulator. This is where delta T variable speed pumping comes into play. This is a pump curve for our new delta T circulator. It'll be coming out this summer. We have the Bumblebee. The Bumblebee's been a fantastic pump for us since its inception. It was an attention getter with the yellow and black color and the cool name, and it's done a grand job for us. The Viridian VT2218 is the next evolution of, no, it's not me, Lyndon, thank you, the next evolution of the Bumblebee, the Viridian 2218. A delta T circulator, kind of on steroids because it does an awful lot more. It's a really neat pump with a lot of cool features that I think you'll like. But the 2218, the reason we call it 2218, highest head 22 gallons a minute, or 22 feet ahead, highest flow, 18 gallons a minute, hence 2218. You'll see that in a couple of other circulators too. The Viridian 2218, the VT2218, is a variable speed delta T circulator. You have a sensor on the water going out to the system. You have a sensor on the common return coming back from the system, far away from the boiler, obviously, so it doesn't get falsified. And it's monitoring the difference in temperature between those two. It doesn't care what the temperature is, it just wants to know the difference, okay? So the system's up and running. Let's say, again, it's 0 degrees, because GPM equals B2H divided by delta T times 500. Remember what happened when the flow was fixed? The delta T had to vary. But what happens if we strive to fix that delta T at what we designed the system for, that 20-degree delta T, or a 10-degree delta T if we designed a radiant floor heating system, a residential radiant system? Okay, what would happen if we fixed that? If we fixed that, okay, and the BTU was what BT load was what the BTU load was, well, the flow has to match the load, right? Which is what a lot of you guys said we wanted in a variable speed pump. We want to match the flow to the load, right? Now the load always changes. It changes with how many zones are open and closed, obviously, but it also changes with the weather, how cold it is outside. So if that load changes and the delta T stays the same, the flow is going to have to fluctuate with the load based on temperature, based on zones opening and closing. And that's simply how delta T works. It's not any more complicated than that. I've seen people online try to paint this thing as something crazy, kooky, revolutionary, nutso idea. It's that simple. GPM equals B2H divided by delta T times 500. You keep the delta T fixed to what you designed the system for. The flow has to vary with the load. It's pretty simple, okay? So let's plot this out. There's our 7 gallons per minute at 5 feet ahead, okay? And there's the system curve. Now, instead of the system adapting to a fixed pump curve, this is unique for the delta T pump, the curve adapts to the needs of the system. So this B line up here, that's the highest, that's the fastest, that's max speed, okay, that's max speed. The A line down at the bottom is minimum speed. What will happen is the VT2218 and the Bumblebee as well will fluidly go between that low speed and high speed wherever it needs to deliver the flow required, to deliver the BTUs required. Okay, so what's going to happen is when this pump comes on, it's going to run at full speed for a few seconds up to a minute or two to establish the delta T as needed. Once it figures that thing out, it's going to find its happy spot to give you that 20-degree delta T. In this example, it will be that new green line, and the system curve intersects the pump curve. We have 7 gallons a minute. We have 5 feet ahead. Now, all zones closed except for that one small one. 1 gallon a minute, 5 feet ahead. Okay, there's your lowest speed under design conditions. We're going to bob back and forth between these two lines. As zones open and close, the pump will be either running here or somewhere in between, maxing out of here. That's how it'll work. The circulator adapts to the needs of the system. That is unique among variable speed circulators. All delta P variable speed circulators are fixed pump curves, okay? And the system does what that pump says, because it has to work on a pump curve, okay? Even with auto-adapt, that's how auto-adapt works. The system adapts to what the pump says to do. Now, when it gets really warm out, say 35 degrees, we only need 3.5 gallons a minute, we'd really be down around here. If you can see where my cursor is, right down around there for a requirement. Well, you know what? It can't work down here. It's going to have to work at minimum speed. So you probably won't have a 20-degree delta T at that point, but you will have the pump running as low as it can. And we don't want the pump running any lower because you still want turbulent flow kind of going through the heat emitters to make sure that you get good heat transfer. So that's why the minimum is what the minimum is. All right, I've been talking really fast for a really long time. Tell me what you think. Okay, tell me what you think. Okay, got a couple questions here about a Lochinvar. We'll get into that, I think, a little bit later on. What happens if you're in a micro load condition? Asked Deb. Yeah, micro loads. You're going to kind of get, depending upon the flow and head. The VT2218 will get down to that spot as quick as possible. If you've got a micro load system with, let's say, a condensing boiler, if you've got real micro loads, no pump in the world is going to be a substitute for a buffer tank, for adding some mass to that, some water content. If you have micro zones, okay, so if your smallest zones are smaller than the lowest firing rate on that ModCon boiler. Personally, I think a buffer tank should be standard equipment, because no circulator is going to eliminate short cycling. Then it's a water content issue. So I would recommend a buffer tank at that point. Circulator is not going to take the place. Now, if you put a buffer tank and a variable speed pump, ooh, and a delta T pump, ooh, now it's about as good as it's going to get. Okay. Question for Michael: will you ever run into excessive velocity situations? Again, GPM equals B2H divided by delta T times 500. As long as all of your pipe is sized according to standard guidelines. This pump is generally going to be running slower than a fixed speed pump anyway. So again, we haven't seen it. You won't run into excessive velocity situations. Again, has not turned into an issue that we have seen in our experience with variable speed residential pumps. We actually introduced the first variable speed residential circulator in North America. Not a lot of people know that, but in 2003 we introduced the OOVR and the OOVS circulators. Variable speed delta T pumping has been around since 2003. So in our lengthy experience here in North America, we have not seen excessive velocity concerns. All right, so why delta T? Again, it's arithmetic. Okay, you keep the delta T fixed, the load varies. The speed has to vary with the load. That's just math. It's just common sense. That's how it works. Look, you're looking up here at the top of the VT2218. We got back to the green and black setting, the green and black color scheme compared to the Bumblebee. The Bumblebee, there you see, it's the one that's sitting behind me. I don't know if you can see it, but it's sitting behind me right there. We're chugging away. But it's a fixed delta T with a variable load. The Viridian has that screen is like an LCD screen. It's a display screen that tells you a lot of really useful information. It doesn't tell you GPM because, quite frankly, no variable speed circulator, regardless of manufacturer, gives you even remotely close information when they show you GPM. A lot of guys like to see it because that's what I'm getting for full. Not even close. Not even close. It has to do with how electrical curves and efficiency curves intersect the pump curves, and it's a 50. And it's generally an estimate based on the high end of the pump curve where it's working at that moment. They're highly inaccurate, whether it's ours, Grundfoss's, anybody's that has that digital readout. The GPM, quite frankly, is virtually useless. So our Viridian will not show that. You see a picture of an early iteration coming up where it does show GPM, but the production models will not have that because they're inaccurate. Okay, let's take a quick look at a couple of questions. If it is silent operation, I'll trade you my Velo Echo. It would make it for the Bumblebee. Bumblebee, interestingly enough, mine's running. It's not making a sound. Some of them made noise. Some of them did not. We are beta testing the VT2218, and we've had a couple that made some noise, but we've been able to isolate why that happens. My dogs are barking. We don't have a webinar without dogs barking. Some of them have made a little bit of noise. If you have one that makes noise, we want it back because we're in the process of isolating that, and I think we pretty much got that one licked. Some Bumblebees made noise, some didn't, oddly enough. So, it's a condensing question from Jim Price. Condensing boiler, 4 zones, better to use zone valves in a delta T pump or 4 delta T pumps? Jim, take your choice, okay? In terms of electrical consumption, you're going to find less overall electrical consumption with 1 delta T pump and 4 zone valves. But some people just like using pumps instead of zone valves, and that's cool. Whatever you want. If you use like the VT2218 as a zone pump, it will in fact vary its speed. Okay, so that's kind of up to you. I don't think there's one that's going to be better than the other in terms of comfort. It's just kind of what you like. Okay. Let's keep looking at some of these questions here. Okay. Jeff Waldman, am I right to say that a delta P circulator is the wrong thing to use on US type systems? Is it your opinion that delta T is always better to use? Right and wrong is an interesting word. I think we're talking about good and better. Delta P does get the job done. It heats, but you'll see some of the shortcomings that it has. And we are introducing a delta P pump. You're going to see it in about a minute. Okay. I think you're talking about a very, very good solution with a delta P pump, and you're talking about a much better solution, a premium grade solution, if you will, with delta T. That is my opinion. Okay with both. Okay with both, but a premium pump is going to be the delta T. Smitty asks about the rotating flanges on the 2218. The beta models do. The production models that you'll see later this year will not have them because of cost issues. We found that people liked them but weren't willing to pay for them. So they will not have rotating flanges in the production modules. Yeah, Morgan, you're right. The GPM and flow rate shown on delta P on any variable speed is a joke. It doesn't matter. Ray, I think we answered your question there. Watch used is nice and necessary for sales, absolutely. Let's see. Is the Bumblebee going to disappear? Yes, eventually. It's done its job. This is a direct replacement for the Bumblebee and a direct improvement on the Bumblebee. So yeah, the Bumblebee will be gone in its way. It will be gone. It's done its job, but this is the next evolution of the Bumblebee. As you see, we still have the picture of the Bumblebee on there. Okay. Very good. Very good. Let's continue. Again, we have lower boiler return water temperature. See, imagine what good that does for cast iron boilers and for ModCon boilers with water content. That certainly helps those achieve their levels. Now here we have the nut grabber. This is a little feature that you'll see on the Circulator. It's a one wrench type of thing, so you don't need to come from a circus family to install it. The flange on the Circulator will grab that nut and hold on to it. And we try to put a lot of wiring room in there for you as well, both with the Bumblebee and also here. We want to make sure there's plenty of room for you to do your wiring, because sausage fingers like me, the little clippy things, these things make a lot more sense and make it easier to do your wiring. And we also, one of the improvements we made was a more secure wiring harness for your sensors, for your supply and return sensors, so that actually screws in place and cannot fall out. That was an improvement we made over the Bumblebee. And here is some of the operating modes. Again, what you're looking at here is flow rate, where it says 7 GPM. That will not be on the production models. This was a beta model. It will not be on the production models. But what it will tell you is the mode. It will tell you what temperature differential you have designed for. It'll tell you the watts. And look at this. It will tell you the supply and return temperature and read it. Now think about that. What a great troubleshooting tool that is. You will actually know the delta T in your system or your zone or however you wish to set that up. So that's kind of a neat package right there. Okay. Let us continue. So the delta T is adjustable 5 to 50 degrees. It is factory set for 20, which is what we have most of. It also has a function where you could make it a fixed speed circulator. It could be one of 4 fixed speeds. So if you wanted to use this, let's say, on an indirect or a fan coil or something where you needed a fixed speed pump, you could set it up. An indirect, you certainly don't want variable speed. That doesn't make any sense. But you could put this on an indirect at its max speed if you wanted to. It would work. It would work and work quite well. We have set point heat. This is cool for you guys that use air handlers. You want to put this pump on an air handler. You can set this to a particular temperature. You can put one sensor, you only use one sensor, you put that in the airstream of the air handler, of the fan coil, or whatever, set it to whatever temperature you want to maintain, and then the pump will adjust its speed to maintain that temperature in the air handler, which is kind of cool. Not too shabby. Has a boiler protection option for in that set point heat arrangement. Can also be used for cooling, which the Bumblebee could not do. So if you have a chilled water application, it's manual changeover from heating to cooling, but you can use this in a chilled water application as well in a variable speed mode. It just goes backwards, okay? But it is a manual changeover, but one pump can do both, and that I think is kind of huge. And then it also has a boiler protection. You can use it as a shunt pump to protect, let's say, a large, light commercial cast iron boiler from flue gas condensation. Okay. Delta P or Delta T is better when? We're going to be getting to that, Nancy. Very good. Thank you for asking that. Morgan, very nice. Okay. Linda says, I'm not familiar. Is there an additional control signal for VS circulators, variable speeds, other than just the on-off mains? A conditional control signal on-off of the mains. Could you elaborate on that question, Linda? I'm not entirely sure what you mean. I want to make sure I get an answer for you, but I'm not entirely sure what you mean. Okay. And here we have... we show the Veridian VT2218 installed in a nice darkened boiler room. All right. Now let's continue. The VR1816, and I like, you see the picture of Phil Silvers and Jonathan Winters there from my all-time favorite movie, It's a Mad, 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 Mad World, because sometimes when people talk about Delta T, Delta P, it starts to sound like a mad, 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 mad world. People just get crazy over, this is better, mine's better, let's just be adults here and just look at it realistically, shall we? The Veridian VR1816 is a pressure-regulated Delta P circulator. But what it does give us is it gives us 3 separate operating modes for a wide variety of applications. In the realm of, variable speed circulators, the VT2218/Bumblebee kind of stand alone as a premium grade. Delta T is the most effective, most comfortable, most efficient way to run any on-off type of system. Okay, that's your premium level circulator. Then you have your standard grade variable speed circulators. The Grundfos Alpha is a standard grade circulator. The Velostratus Echo standard grade. The Viridian fits into that slot as well. It's a standard grade variable speed circulator. It does what it does, and it's limited in what it does, but it does what it does and it does it very well. Where would you use this? What are the applications? As we said before, you could use it for zone valves. You can use it as a zone pump, but it's going to be limited in what it can do. Okay, it'll vary its speed in a zone valve application, but it's a fixed pump curve pump, so it limits what it can do, as we'll see. As a zone pump, it's a fixed speed pump. It doesn't change its speed any, but it's an electrically efficient one. So it does do something for you, but it's electrical savings primarily in both of those applications. You put it in the proportional delta P mode with thermostatic radiator valves. Now it sings and dances. Okay, now it's doing what it was born to do. Okay, so again, it's knowing what the right application for it is and what you're doing and where you're doing it. It's a standard grade, like the Alpha, like the Stratus Eco, a standard grade variable speed pump. The Delta T2218, it's going to be your premium level, high performance circulator. Let's get into the discussion here. Yeah, I'm going to go back one. If you look right here on the faceplate, you see the 3 different operating modes. The first operating mode, way over here on the right, you see it says min-max. Think of that as a volume dial. You can turn it up, you can turn it down. You can manually adjust infinitely between minimum and maximum a fixed speed for the pump. So it's an infinitely variable fixed speed pump, if that makes sense to you. So it's a volume dial. Dial it into the speed you want. Talking about zone pumping, that's a pretty good way to go. Talk about other applications. Maybe you want to use it for an indirect. Turn that sucker to max, okay? Maybe you want to use it in a small zone or a small application. Maybe you figure out what the flow and head is there and you adjust it accordingly. Okay, you'll see the 3 dots is min, max, and then 3 dots. We'll show you what the programming is like in a moment. The next section, that middle section at the top of the arc, you see what looks like an L and then a flat line going across it. That's your constant pressure differential mode. If you were to use this as a zone valve circulator or as a zone pump circulator, that's the mode you would use, one of the 3 presets, and we'll show you that in a moment. And then far to the left, you see the L with that diagonal downslope. That's your proportional delta P mode. That's what the mode you would use if you were using it with thermostatic radiator valves. Let's jump in and really dive into this. Here you have, there's an LED. Let me go back here. You see this little LED right here, the status LED? That thing's kind of cool. That LED will change color based on the mode. So it's one LED, 3 different colors. If we are in the the infinite variable mode, meaning far to the right where we set a fixed speed, the LED will be in the blue mode. And you'll see, based on what we showed, the 3 different settings. If we turn this thing all the way, I mean, we peg it all the way to 11 because it's 1 louder. If we peg it all the way to max, you'll see it's going to run at that max pump curve here, the top blue line. That's its maximum speed. That is roughly the equivalent of a 0015 3-speed pump or Grundfos 1558 at high speed. It's roughly equivalent. 15 has a little bit higher flow and head. So that's where you'll be there. If we go to that first dot, okay, this dot right here, we go to this dot right here, that's roughly the 008 pump curve or 0015 medium speed pump curve. You see out here the sweet spot is really not all that different from max speed. We go to the middle dot. Now we're starting to make a difference here. That's that's roughly a 007 pump curve, more or less. The 0015 at low speed. The first dot is a 006, and again, you'd be amazed how often that's as much pump as you need for a zone pump. You'd be amazed if you actually did the math. You'd be amazed how much that's all the pump you need. And then if we go to the minimum setting, now we're down here, which is roughly the equivalent of a 003. So you figure your flow and head, and you see where you're at. So let's take a look at the job we were looking at earlier, 7 gallons a minute, 5 feet ahead with zone valves. Okay, there's Jonathan Winters representing 7 gallons a minute at 5 feet ahead. That's all zones calling. All right, and here we have one zone calling, 1 gallon a minute at 5 feet ahead. So clearly, if I use that lowest dot setting, the 006 setting, that's not going to be enough pump under design conditions. Be enough pump when I only have one zone calling, but I have more zones calling, simply not going to be enough pump. So we can't set it there. And I can see from the lines here, the 007, the middle dot is more pump than I need. But I see where Jonathan Winters is. That's looking like it's kind of halfway between the minimum, the first dot and the second dot. That gives me an idea of where I can put the dot. Okay. If I'm at 50% load, now here's where we're going to see where this pump is nice under design conditions, but when it's mounted in the design, the delta T is going to shrink. Okay. There we are at 3.5 gallons a minute at a little less than a foot ahead. That's 50% load if it's 35 degrees outside. That's where we want to be. Okay. If we were to set this up in that mode, okay, basically I'd move the dial somewhere between those first two dots, and that's the pump curve I'd be working on. So I'd set that up for my max pump curve under design conditions, and that's the pump curve that it'll run at all the time. Okay, and that's the power consumption it'll have all the time. All right. When I'm at 35 degrees outside, this is where I want to be. This is where I'm going to be. I'm still going to be getting 7 gallons a minute. My delta T is going to be about 10 degrees. It's not going to be 20, but it's going to be better than it was if I had a fixed speed pump at max speed. That's the benefit here. You can dial it into where you need it to be. Okay. The second operating mode, the middle operating mode, that's constant pressure. Constant pressure. Okay. And you'll have an orange LED. Constant pressure. What constant pressure means is it turns this thing into a flat curve pump. It's not any more magical than that. Instead of a steep curve, it makes it a flat curve pump. Now, in a zone valve application, the speed will vary depending upon where on this flat curve the system curve intersects. That's how it will vary its speed. In a zone pump application, it's going to work on where the system curve intersects the pump curve, and it's not a variable speed pump, it's a fixed speed pump that is ECM. That's a very important thing to remember. A delta P pump as a zone pump is not a variable speed pump. It finds its happy spot, and that's how fast it goes. Important safety note. Okay, but depending upon which one of these I choose, I'm either going to run at the basically it's going to be a 006, a 007, or a 008. Okay, the red part's the variable speed part. If I pick the 007 curve here, the middle one, and my system curve intersected the pump curve out here on the blue line, the pump's going to run at full speed. The red part's the variable speed part. So let's take a look at that same 7 and 5 system. 7 gallons a minute, 5 feet ahead. All right, hey, looky-loo, I'm right there. 1 gallon a minute, 5 feet ahead. Hey, looky-loo, I'm right there. That's my setting. I set that to the lowest setting. That's my 5 feet ahead, the worst it's ever going to be. Here, where this is the intersection point with all zones calling, this is the intersection point with one zone calling. Any other combination of zones will be somewhere in between the two, and that's where the pump will vary its speed. 35 degrees outside, 50% load, this is where I need to be. I'm still going to be up here, though. It's still going to be up here. So the delta T's will be smaller. Delta T's are going to be a darn sight better with a delta T pump that's going to reduce the short cycle. Okay. I hope that makes sense at you. Again, a lot of information shooting that at you. I want to make sure you get it. Okay. But in this case, I'd set it at the low speed. Now, proportional delta P, this is your TRV application, okay? That you have inclining or declining pump curves. As flow goes down, head goes down. That's your thermostatic radiator valve job, okay? As those things choke down, as they aren't getting satisfied, I don't need as much flow. So if I don't need as much flow, I'll just slow down, okay? That's how it reacts, okay? If I were to use this in a zone valve application, you will see the challenge. Okay, here's 7 gallons a minute at 5 feet ahead. That falls right at the low speed. Hey, if I didn't know any better, that's what I'd set it at, right? But look at 1 gallon a minute at 5 feet ahead. My requirements are greater than that pump curve. The pump's not going to know to do anything any differently. And this is true with an auto-adapt type of thing. Well, it doesn't know to change, okay? It doesn't know to change. It just finds that it adapts to that whatever lowest one it needs to be, and that's it. It doesn't know to adapt here. So that's where I would be. When I only have one zone calling, I wouldn't necessarily have enough to satisfy the load. To make this work, I'd really have to go to that medium speed. And again, now with all zones calling, I'd probably be out here someplace on the pump curve out here, pump's going to be running at full speed, and it's going to do that in October, it's going to do that in January, it's going to do that in September. Okay, so again, your proportional delta P with zone valves, just not the right application. And again, here we have 3.5 gallons a minute, 50% load. Yeah, now it's all going to work at this low speed right here. It's going to intersect this pump curve somewhere along this line all year long. The challenge you're going to find is if you had a combination of zones when it's really cold out, you might not have the flow you need to make them happy. That's the weakness of proportional delta P. With thermostatic radiator valves, hey, we're good. Okay, we're really good, and that'll work out well for you. And again, we'll look at this with the VT2218. This is where it's going to work for that 7 gallons at 5 job, 50% load. This is where it wants to be. It'll be working on its minimum speed. That's just the way it is. Okay, very, very good. All righty. Now programming. I want to run through programming real quick because we're running a little bit over time. Our goal here is to keep it simple. If you go ahead and do the math and really pinpoint out, which I recommend you do, okay, you do all the math, you can actually pinpoint your programming very, very nicely here. These are some guidelines just to keep it simple. The constant pressure settings when you're using, for zone pumping, if the total length is around 85 feet or so, use that first setting, that 5 foot ahead setting. Okay, it's called CP1. It'll actually say 5 on the production models. 165 foot total length for a zone. You set it at the middle one. Okay, and up to 250 feet, you can set it at 15 feet ahead. Here you can see the 5, 10, 15 right here. That's where you'd set those. Again, it's a broad generalization. Always better to do the math because you will more than likely find that 5 foot ahead is going to cover an awful lot of applications. Future webinar, we'll go through how to do that and how to set that. But what you're doing is you're setting a fixed pump curve. Again, the delta T, the pump curve is going to move for you. Here, you're setting a fixed pump curve, and you got to make sure you know what it is. Okay, and this is based on the measured length times 1.5 times 0.04. That's where we come up with these estimates. Okay, and these are just that, they're estimates. And again, here's where you wind up. Your 00, here's your 006, for that shorter zone, the medium zone, 007, longer zone, right there. Okay, very good. Infinite adjust, that minimum speed. Again, it's on the pump curves that we saw earlier. That minimum looks at like a 003. The low dots, 006, medium, 007, high, 008. Max would be about a 0015 at high speed. Okay. And if you were to actually calculate the flow and head, again, you can really pinpoint all of that for yourself. Whew, boy, that was an awful lot of stuff thrown at you at once. How do you feel about all that? How was the pace? Was it good? Was it useful? I mean, did you find this stuff helpful? Now, I got an awful lot of questions here I did not get to. I want to get to all those, and I want you to keep throwing your questions out there. So, and I'll stay on here, gang, for as long as you would like, and answer as many questions as you would like. But man, we did certainly cover an awful lot of ground. Okay, so let's take a look here at some of these questions. We had: is the Bumblebee going to disappear? Eventually, yes, Curtis, it will be. It's lived its life. It's being upgraded with the VT2218. Nancy Imhoff asks: Delta T or Delta P, what is better when? Let me know, Nancy, if we answered that question for you. I think if you have thermostatic radiator valves, I think the simplest approach for you is going to be the Delta P, the VR1816 in that proportional mode. I think that's going to be the most sensible application for you and the easiest. Okay, the zone valve, zone pumping applications, by any measurable means, Delta T is going to be the better solution, the premium solution, most effective, efficient, economical solution to that. There'll be a price difference between the two, so you have to wade through that as well. And there are some people that just simply don't want to install sensors. The Delta T pump is going to require a sensor, one on the supply, one on the return. If you have zone pumping, that's one set of sensors for each pump on each individual zone. The Delta P circulator does not require any additional sensors. Again, some people want to just get in, get out, go away. They call it good. Some people simply want to meet, like in the Northeast, if they're replacing a bad circulator, they simply want to take advantage of the incentives. They don't particularly care about anything else or optimizing it. What we fully expect to see is a lot of the VR1816s installed in that application because they meet the requirements for the incentives. running at full speed. That's just the way it is. Okay, now it's just a more efficient fixed-speed circulator. Okay, so either or. You know, I think I hope that answers your question. Please let me know. It's like, what's better? Yeah, I think if we're talking about putting together a Christmas, New Year's ban on imports all rolled into one solution, the Delta T VR 1816 has no peer. It is a premium grade pump. If we're looking in that mucky middle of the road kind of thing, well, then you have the VR 1816, which is multifunctional that can fit into that middle of the road application. Okay, let's see. Again, Lyndon, I think you're trying to give me that information. The wires to the pump are the following. We have just your electric to your relay to turn the pump on and off, and then 2 sensors. That's all the wiring involved with a Delta T pump. You can wire like any pump. There's nothing unique to it. There's no additional controls wiring. All the controls inside. Wire it up to a pump relay or a zone valve control just to turn it on and off, just to turn the pump on, turn the pump off. The only additional wiring is your 2 sensors, 18 or 10K resistors. Very simple. Let me know if that answers your question. Is this pump an attempt to provide one pump for all applications? Are you asking Curtis about the VR? It's not an attempt. I think it has different applications. I don't think there's one pump for all applications. I really don't, and I think it's dangerous to think that. We want the right pump for the right job. The VR, if you wanted one pump for everything, the VT2218 might be the closest you could come. Some instances, it's more pump than you need, more controls than you may necessarily want on a job. Again, if it's a budget job, that sort of thing may not be what you're looking at. So no, I would say no, because personally, I don't believe in one pump for all applications. I think that's wishful thinking, and I think it's poor salesmanship or poor marketing by any manufacturer that says that, because there is no one pump for all applications. Just pick the right pump for the job. That's why they have all different kinds of pumps. What's the right pump for this job? Just as long as you know VR18 will do the job in a zone valve or zone pump application, it'll get her done. If your definition of success is nobody's freezing to death on my watch, yeah, VR 1816 is going to get it done. But if you aspire to higher, if you want to make sure you're giving your customer the economy of operation, the efficiency that they would really like, the higher performing system, then the VT 2218 is your solution. So again, it's really what fits into that customer's project, what fits into the budget, okay, are also different things to think about. Do you want credit for Minnesota mechanical? Morgan, if you email me with the requirements, or if there's a form that you have that I need to sign, I'm happy to do it. We don't have anything officially done, but if they just need something signed, I'm happy to do it. Just let me know, okay? So proportional delta P is good for TRVs. Proportional delta P was invented for TRVs. That's its job. Okay. Applying proportional delta P to anything else is kind of foolish, in my opinion. It was meant for, designed for, intended for thermostatic radiator valves in Europe because that's what they use. You know, it's this whole thing. Well, we use it for these other things. It's meant for thermostatic radiator valves. That's its job. Okay. That's its job. Okay. Maybe we could talk, check, email after. Sure, any of those, Sean, any of those are fine. I will type in my email address for anybody who would like it. I'm going to send this to everybody, gmail.com. I'm going to send that to all. You should see it in your questions and answer section. Be happy to do that. So, yeah, just keep that and feel free to email me. You'll also be getting an email from me fairly soon about for follow-up. If you have a baseboard system and are using a Delta T pump with outdoor reset, you'll be sending lower water temperature through the baseboard. Will this require the system to run longer to maintain the required temperature? Delta T doesn't care what the water temperature is. Doesn't care what it is. It only cares about the difference between the two. That's it. Sometimes there are people who will say, because I'm running lower water temperature, I would ordinarily have longer run times for my zones. Yeah, you probably would have longer run times for your zones, whether you had a fixed speed pump or a variable speed pump. Doesn't make any difference. Okay? The thing about having the right flow for the right at the right time probably might have a little bit longer run time, but you are bringing back lower water temperature to the boiler, so the boiler has longer run times. It has fewer cycles but longer cycles, which is what you want. The boiler is going to work better and more efficiently and more effectively. And in a condensing boiler application, if we're bringing back lower water temperatures, that's better for the boiler, isn't it? In any way, shape, or form, there's no arguments there. Okay, Michael asked a question. What would you recommend if you have, boy, there are a lot of questions. Way to go, guys. Keep them coming. I love it. What would you recommend if you had a system with both high head zones and low head zones with zone valves and one pump? That's always fun, okay, because the low head zones might get the flow, and that's with fixed speed pump, variable speed pump, delta P, delta T, doesn't make any difference. They're going to behave in pretty much the same way. Okay, a lot of guys say, well, delta P will take care of that. That's wishful thinking. How is it going to? It can't. Okay, the low head zones are probably going to get the flow first and satisfy the high head zones later. You're playing a shell game with your zones. It happens, okay? Unless you make them all exactly the same length, this is what's going to happen. So the shorter lower head zones, whether you have a fixed speed pump, a delta T pump, or a delta P pump, all three, they're all going to behave pretty much the same because delta P, you've got a fixed pump curve. Don't forget that. The low head zones are going to satisfy first, then the longer higher head zones are going to satisfy. You run into a problem if that low head zone keeps opening before the high head zones are satisfied. That happens in any system that is not properly balanced or not properly installed. With any pump, delta T, delta P, delta, no delta at all, fixed speed, you want to try and get the zones within 10–20% of each other in terms of length. That's probably the best way to go about it. Sometimes it's not possible. That's when balancing valves come into play if you need those. But that's the reality of the situation. Let me know, Michael, if that answered your question. It's a really, really good one. Okay, very good. You like the short cycle one, Sean. Good, I'm glad you did. All righty. Let's see what else we have. Pace is good, very good. Okay, good, thank you. When using, okay, here's one from George Wise. When using the new green pump and using delta P, do you need any temperature sensor? Again, the VR1816, the delta P pump, no additional sensors are required. Everything that pump needs is inside the pump. Again, that pump will vary its speed based on resistance against the impeller. Okay, more resistance, it'll go slower. Less resistance, it'll go faster. Okay. Are the Viridian pumps available right now? The VR1816 is being introduced early spring, okay, April, May, probably April. We are beta testing it up in the Northeast. If you're up in the Northeast, you may be able to get one to try. The VT2218 early midsummer, perhaps. I just want to get this information out to you because you will be seeing them sooner rather than later. The reason we're doing the webinar now is because we introduced them at the AHR Expo in Chicago just this past week. So they're out there in the public, so I wanted to make sure you guys were up on them. As a note, threading the sensor wires through the opening can be very tight. Yeah, it can be, but we just don't want to have, we don't want them to pull out like the plug to pull out. So yeah, it's got to be better to disassemble the whole thing, assemble it, put the plug in, put the cover on, and make that work rather than trying to wire it through there. Take the whole thing out and make it work. Very good. Yeah, this is a Friday afternoon. Yeah, I was aware. Morgan, you live in Prior Lake? Yeah. Okay, let's do that. I'm up for that. Let me know. Maybe we'll go over to Captain Jack's or something, right? Oh, and if you have any questions for Dave Holdorf, who is also who is our Northeast Regional Trainer, and by all accounts, smarter than I am, just not as good looking, and he's a Giants fan, so we really don't like each other. Dave Holdorf is here as well. If you'd like to email Dave, I'm going to give you his email, davehall@taco-hvac.com, and I'm going to send that to everybody. So write that down and do that. Very good. Curtis Reynolds, very good. You're going to go snow blow a bunch of snow. I hear you, bud. Question from Jim Price. With a condensing boiler with a primary and secondary loop with 4 zones, if I use 4 zone sentries and a single delta T pump and a pressure differential valve, I want to go out at 155 and come back at 135. How will performance be as different zones open and close? 2 zones are short and 2 zones are long. I'm not sure the pressure differential bypass valve is going to help you much here. Dave, if you have a thought on that, throw that in. I'm not sure a pressure differential bypass valve is going to be of much use. But what will happen, yeah, I don't think it's going to be of much use anyway, so probably not necessary. But delta, as we said before, Jim, delta T, delta P, fixed speed, what's going to happen? The short zones are going to satisfy first. The longer zones are going to satisfy later. Just the way it is. And with the delta T pump, the water is going to go out at 155 and come back at 135. but the shorter zones are going to satisfy first because there's lower head, just the way it is. Okay? And again, it would do that. Delta T, Delta P, or fixed P. There's no difference. A lot of people think, oh, Delta P will take care of that. How? It can't. It doesn't know to. It can't. That's why the whole smart pump thing to me is a bad name, because they're not that smart. Okay, they can't a smart pump can't make up for bad piping or just the piping that comes when you're doing a job and two zones happen to be short and two zones happen to be long. That's not bad piping. That just is what it is. These pumps don't figure that out. And the whole smart pump thing drives me batty because, oh, I don't have to know anything. I can do whatever I want. A pump will figure it out. No, it won't. It can't. Okay? Don't fall into that smart pump trap. It's just plain wrong. Dean Martin asks, first Dean Martin says, everybody loves somebody sometime, right? Except the dogs. Will they be coming to Canada at the same time frame? Yes, absolutely. That is the plan for us to come to Canada within the same time frame. Easy. Quiet. All right. Question from Sean. What is the pump speed control make and model to be used with the Lochinvar KVN400 and a Takeo 1635 boiler pump? Sean, I cannot answer that for you. That is on our commercial side. I'm a residential guy, so I'm not as up on that end of the business as those guys who are on that end of the business. In fact, Takeo actually has two separate entities on the commercial and the residential side. Dave may know this because Dave, again, is smarter than I am, but I couldn't answer that for you. You need to talk to someone from our commercial division. Sorry, I wish I could help you out more. What is the warranty on the pump and the expected life of the pump? Warranty is 3 years, standard warranty. As far as expected life, that depends on the water, gang. It really depends on the water. If the water is not treated and it goes into a system with dissimilar metals, it's going to cause corrosion. That magnet's going to go and ours, Velos, Grundfosses, B&Gs, anybody's is going to have a shorter life. Treating the water is becoming so much more important nowadays. We have a webinar archived on the neighborhood, and you all get info on that, on water treatment, done by Bruce Marshall on behalf of Fernox. Maybe the single most important issue going forward, with ModCon boilers being attached to older systems, with anything with dissimilar metals is going to cause corrosion, along with these circulators. If you don't treat the water, you're going to kill that pump prematurely, guaranteed, and that's anybody's. Okay? So treat the water. That's very, very important. Okay. Are the new Viridians web-based? What points can you see from the pump controller? That, again, those are the commercial Viridians. These are not web-based. These are the simple residential models who use the same name. The commercial Viridians are web-based. You can look. You don't need the web to use them or program them, but you can look them up online, and they'll tell you run time. They'll tell you the maximum head it's running at. They'll tell you all different kinds of information. Again, more on the commercial side, not in my ballpark, but that's it does give you a whole. They have their own particular web page. You can look it up and see exactly what it's doing. Okay. It would impede the search from propeller operation. The 1860 would run full out. The 2218 would slow down too much and never speed up for demand. Dave, there's a question. There's an answer there, and to a question. Just tell me what question you're answering, so I can do that. Give them a good look. Somebody just walked in and is letting the dogs out. I wonder if that's my son. Is that you, David? That's my son, David. He's going to let the dogs out for me. Thank you. Very good, very good. Okay. Keep those cards and letters and questions coming in. Oh, if a pressure differential bypass is used. Okay, that's the question regarding the pressure differential bypass valve. Again, I don't think there would be a reason to use a pressure differential bypass valve, Jim, in the scenario you suggested. Just it wouldn't help you any. Okay, it wouldn't help you any. Very good, very good. Okay, and Fernox, Morgan's is using Fernox in all of our boiler work now. Again, any kind of boiler treatment, boiler water treatment is a really, really, really good thing, especially today, because again, you don't want to get the more gunk that gets into the heat exchangers on the inside on these small little ModCon boilers. That's going to shorten the life and really reduce the overall efficiency. It kind of builds up in those little passageways, and then more heat, they tend to crack and corrode. We can actually see, when we look at it, see where the sludge is built up. So you want to be able to, you got to clean that out, and then you want to treat the water to minimize the corrosion buildup over time. And if I don't know if you've ever seen those magnetic filters or those magnetic system cleaners, it's just amazing what they can do. They're really powerful magnet. You need a more powerful magnet than the one that's in the pump is really what you're looking for. And the stuff just collects all that crap, and you can flush it out and clean it. It's a very important thing to do in systems going forward. All righty, great. Well, what time is it? We've been at this for an hour and a half. It seems like just yesterday when we